Hi everyone, welcome to this video on the universal wave equation. The universal wave equation is one of those things we take for granted, but it's very, very important. We use it all the time when analyzing wave behavior, and it's very significant that way. It's called universal because it applies to any kind of wave, whether it's a light wave, a sound wave, a mechanical wave. It applies to any wave. So the thing to remember for the universal wave equation, a fundamental concept, is that when you have a wave, the speed of the wave is constant as long as the substance or medium it travels through remains constant as well. So if you remember last year, you looked at the speed of light. And the speed of light is constant unless it entered a new medium, and then it would slow down or speed up. So for example, a light traveling in air would hit water, it would slow down as a result. So we look at the situation of when the light or the wave is in the same substance. So the speed is not changing, it's constant. So to figure out the speed of the wave, you have to know a couple of things. Well, first of all, let's look at a typical wave we have over here. What I have is a single cycle, one complete motion of a transverse wave. So we're going to call this one cycle. And this one cycle, what happens is the wave travels a complete distance of one wavelength. So the distance of one cycle is one wavelength. Also, if you recall from before, the time it takes for one complete cycle of motion is referred to as the period. The amount of time it takes for the motion to repeat itself. And the other thing that we know is this. Because the speed of the wave is constant, we can use the constant motion equation, which is equal to the displacement or distance over time. So in this case, the distance is going to be my wavelength, so wavelength, and the time is going to be my period. I'm also going to throw another twist in here. We also know that the period is the reciprocal of the frequency, and frequency is the reciprocal of the period. So look what we have here. If I rewrite this equation, we have this. Wavelength times 1 over period, and we know this is the same thing as frequency. So I can rewrite my equation. Speed is equal to the wavelength times the frequency. And that is the universal wave equation. So let's write it down here. So the speed of a wave is equal to the wavelength multiplied by the frequency. Now, we have to be careful with units. We always measure frequency in hertz or 1 over seconds. We have to measure wavelength in meters. And as a result, the speed is going to always be meters per second. Right? So again, this is the universal wave equation. It applies to any type of wave. Let's look at a quick example here. So what I have here is I've got the sound wave of a bat, and it's 55,000 hertz, which is way beyond our hearing range. And the speed of sound is 350 meters per second in this particular situation. And what we want to know is what's the wavelength going to be of the sound. So we've got our givens. I rewrote the given here without scientific notation. There's my speed. I know my equation. Standard universal wave equation is v equals lambda times f. Plug my values in. I'm going to solve for lambda or wavelength, and we end up with 0.0064 meters. And this is about 6.4 millimeters, which is pretty cool. It's about the thickness of a pencil. Now, sound waves are actually longitudinal waves, which are a bunch of compressions. And the compressions in this case are all 6.4 millimeters apart. This is what a sound wave given off by a bat would actually look like if you're able to see it. Pretty cool stuff. All right, now, this wave, as I said, is universal. So this equation is universal. It can be used for any wave. So if we have an electromagnetic wave, something like light, radio, infrared, X-rays, we can use the same equation. The only thing to remember then is that the speed of these waves in air and in vacuum is 3.00 times 10 to the 8th meters per second. So you ever have a situation, I'm asking you to solve something and you're missing the speed, check to see if it's an electromagnetic wave. You know then that the speed is going to be the speed of light. So here's the deal. Here's a great example. What's the wavelength of a microwave oven that has a frequency of 2.65 gigahertz? This is the actual frequency of microwaves. Well, let's look at what we have here. I have the speed of light. I really don't have it, but I know I'm dealing with it because it's a microwave, and they're traveling at the speed of light. I also have the frequency. I can rewrite it as a standard notation, or I can just write it down like this. 2.65, and I know giga means 10 to the 9th, so 10 to the 9th hertz. That's what giga is. It means billion hertz. So we're going to substitute those values into the universal wave equation. So I solved here for wavelength. I divided both sides by frequency. So I'm taking my speed of light divided by the frequency, 2.65 times 10 to the 9th hertz, or 2.65 gigahertz, end up with a value of 0.113 meters. So basically the wavelength of that microwave oven is 11.3 centimeters. So, 0.3. And if I looked at this, real life, you'd have a wave that looks something like this. That would be the wavelength of a microwave coming from your microwave oven. And the neat application. So that's it for the universal wave equation. Very simple equation, lots of power within it though.